So I have 25 minutes or 30 minutes.
It is, including the question session, it is 30 minutes. So if you maybe finish by 27, 28 minutes, I think we'll have 2-3 minutes for some question and answer. That's the plan.
Okay.
So once again, welcome participants. Now we have the second session. This session is chaired by Professor A. Swaminathan, Professor of Mathematics, Indian Institute of Technology, Roorkee. So without wasting time, I welcome Professor Swaminathan to chair this session.
Thanks, Dr. Dilip. Thanks for giving me the opportunity. I thank the organizers of SSFA for giving me an opportunity to chair a session, and in particular, the chair a session where there is 3 nice talks available there. To start with, the first talk is by Professor Walter van Asch. He is from the Catholic University Leuven, Belgium. Even though we say he's from Catholic University Leuven, Belgium, he is from everywhere, wherever orthogonal polynomials and special functions are there. And he was the chairperson of the OPSF group, and he is one of the important members. So that I generally meet him in every OPSF conferences where he is the lead person in making this every conference successful. In fact, even he has visited once Roorkee, and in the conference which he organized, he was the keynote speaker there. So, and my association with him is a long time one in this sense. And Professor Walter van Asch is going to speak on the multiple orthogonal polynomials and the number pi. Over to Professor Walter. Professor Walter, please.
Okay, thank you, Abu, for this nice introduction. And I also thank the people from the Society of Special Functions and Applications for inviting me here to give a talk. It's a pity I can't be in India right now because here in Belgium it's freezing. But let's see what I can try to explain you. So special functions appear in these multiple orthogonal polynomials. And of course, there's a special number, also the number pi, which everybody likes. So let's see what we can do. What I will do is I will show some recent results about the irrationality measure of this number pi. And I will show that it's related to Hermite-Padé approximation. And Hermite-Padé approximation, that depends on multiple orthogonal polynomials. Just like Padé approximation is very closely related to orthogonal polynomials. These recent results are not mine. They're results from some other people that I will mention, but the connection with Hermite-Padé approximation and the multiple orthogonal polynomials is a new angle. What I will do, my specialty is actually doing asymptotics, is to analyze the corresponding Hermite-Padé approximation problem when the degree of the polynomial tends to infinity, and that will give you the required upper bound for the irrationality measure of pi. So the warning is that I will not obtain a new irrationality measure. I will stick to the ones that have been found very recently, but I will have this connection with special functions. Now for the number pi, of course, there are lots of results known for pi. We know that pi is approximately 22/7, and that goes back to Archimedes. This is 250 BC. And in fact, Archimedes showed these nice bounds over here. We also know that pi is irrational. That also dates back 250 years to Lambert, and that it's transcendental. And that goes back to Lindemann 200 years ago, well, 150 years ago. And very recently, like this year, 62.8 trillion digits have been computed for pi. So you think we know a lot about pi, but in fact, we don't know so much about pi. Well, in practice, we only need this 22/7 or 3.14 for any practical calculation. But what do we not know about pi? We don't know its continued fraction, just to make a connection with the previous talk. At least we know some continued fractions for pi, but not the regular continued fraction, which has the numerator equal to 1 all the time. We don't even know a lot of things about the decimal expansion of pi. For instance, the number 7, we don't know whether it will appear infinitely often in the decimal expansion or any other number. And even more, we don't know whether pi is a normal number, meaning that every decimal appears with a frequency 1/10. And that's in the expansion for at base 10. But even at base 2 or 3 or 4, we don't know whether it will be normal in any of these bases. And what I will be talking about is we don't even know how well pi can be approximated by rational numbers. So we do approximate pi all the time by rational numbers, but we don't really know how well it can be approximated. And to measure the how well you can approximate pi by rational numbers, we use this irrationality measure. It is a measure that shows you how well it can be approximated by rational numbers. And here's the definition. We call it mu of x if x is a real number. So you want to approximate x by rational numbers. The approximation should not be exact. It's a strict approximation. And it must be bounded from above by 1/b to the power r. And if there are infinitely many solutions A of B for these inequalities, then you say that x can be approximated at order r by rationals. So the bigger r is, the smaller the upper bound over here, the better you can approximate x by rational numbers. So the biggest one for which this holds is called the measure of irrationality. And so we don't know what the measure of irrationality for pi is, but we do know some other things. So if x is a rational number, then the measure of irrationality is just going to be 1. And then you make a jump. If x is not a rational number, if it's irrational, then the measure of irrationality is greater than or equal to 2. So you jump from 1 to 2. What is also known is x is algebraic. So a solution of an algebraic equation or a polynomial equation with integer coefficients, then the measure of irrationality is going to be 2. That is not an easy result. In fact, Roth proved it in 1955, and he was awarded the Fields Medal for this result and others, of course. But for the number e, the basis for the natural logarithm or the natural exponential, the measure of irrationality is 2. And so e is a transcendental number, but it still has the same measure of irrationality than an algebraic number. But we don't know what it is for pi. So what we want to do is find some upper bounds. Very likely it's also going to be 2, because almost every real number will have measure of irrationality 2. But it's not so sure that it will be true for pi, because there is a chance that you can find a thin subsequence for which the approximations are going to be better than order 2. Okay, so how do we prove upper bounds for the measure of irrationality? Well, I can use a result by the brothers Borwein, Jonathan and Peter Borwein from 1987. It's in their book on the AGM, the arithmetic and geometric mean. So if you can find, and it's constructive, so if you can find integers Pn and Qn such that Pn over Qn is a rational approximant to x of order 1 plus r, where r is a number between 0 and 1, then the measure of irrationality of x is going to be bounded from below by basically 1 plus r, but since r is between 0 and 1, it will immediately jump to 2. But the important thing is the upper bound is that it's going to be bounded from above by 1 plus 1 over r. So by constructing rational approximants of a certain order, you may find upper bounds for the measure of irrationality. In practice, this is done in the following way. You use the rational approximants Pn and Qn that we use over here. And then you try to figure out the asymptotic behavior of the numerator and the denominator. So if the numerator, the lim sup of the nth root is converging to a number a which is bigger than 1, so the Qn, the denominator, is going to grow exponentially fast with a basis a. And if the error that you make over here, or this linear error, the nth root, is going to converge to a number 1 over b, which is strictly less than 1, so this is going to converge exponentially fast to 0, then the numbers a and b can be combined to find this number r over here, and you get this upper bound for the measure of irrationality. It's going to be 1 plus, and 1 over r is going to be log a divided by log b. So here is where asymptotics comes in. So you have to construct these rational approximants. You have to do this nth root asymptotics for the denominator and for the error of rational approximation. And then you get this upper bound for the measure of irrationality. So in a way, and this is quite amazing, usually irrationality proofs are proofs by contradiction. Because you certainly have to prove that something does not exist. But these kind of proofs are constructive proofs, because you construct rational approximants, and with those rational approximants, you have this constructive upper bound. And so let me show you a proof that pi is irrational. Everybody knows that pi is irrational, but that also gives an upper bound for the measure of irrationality. It's not an optimal proof, but just to give you some idea, and the idea will be expanded upon later on to get better upper bounds for the measure of irrationality. So you start with this integral over here. It's an integral from -1 to 1 of this rational function, which depends on n, 2n in the numerator and 3n plus 1 in the denominator. It has zeros in the points 0, 1, and -1, and it has a pole in the point I. Minus I guess, yeah. Well, if you calculate some of these values for certain numbers of n, you will figure out that this integral is always this linear combination of pi with these rational numbers a and b and cn. So you can find a and b and cn, which are integers, such static a n is always going to be of this form. And then that allows you to give some rational approximants for pi. However, we need to figure out a little bit more about a and b and cn to make it into a rational approximation. This integral was suggested by Fritz Berkers in 2000, who was trying to explain a proof of a good upper bound by Hatta, which I will tell you about a little bit later. Now, some number theory comes in, some basic number theory, combinatorics, and I will always denote this in blue letters when number theory is coming in, and all the rest will be analysis or approximation. So you can figure out that the an and the bn, they are both divisible by this power of 2. One can also figure out that the cn is a divisor of the least common multiple of all the integers from 2 to 3n. And the 3n comes from this denominator 3n. And you can also figure out, and this is a lot harder, that cn contains no prime factors between 3n over 2 and 2n. This is important because then you can multiply this kn by a number which I will call dn, which is the least common multiple of these numbers from 2 to 3n, in which you take away all the primes between 3n over 2 and 2n. If you do that and multiply the an by this dn and you divide away this power of 2, and the same, if you multiply the bn by this dn and divide by this 2 to the power n over 2, then this becomes an integer. So the pn becomes an integer. The an was already an integer, and I divide away this factor and I multiply by another integer, so that stays an integer. And so this number now becomes an integer times pi minus pn. So pn over qn is now a rational approximant for pi. And then to show how that it converges well, we need to work out what is the asymptotic behavior of the qn and what is the asymptotic behavior of this quantity kn multiplied by these numbers. Well, for the kn, here is the kn. We can estimate what kn is going to be by taking absolute values, take the absolute value inside the integral, and then find the maximum of the integrand on the interval -1 and 1. Okay, so that maximum of the integrand in the interval -1, 1 is going to be this small number. If I raise it to the power n, then that would be the integrand for the kn. So raise this to the power n, and then I'm going to take roots, nth roots. So I'm going to end up with this number again. Okay. Then some elementary number theory, like the prime number theorem, will tell you that the nth root asymptotics for the dn is going to be e to the power 5 over 2. So you get the nth root asymptotics of this least common multiple, and you would have to use the nth root asymptotics of all the primes between 3n over 2 and 2n. So combined together, that will give you that number. And then the square root of 2 is the nth root asymptotics of this power of 2. So we have the asymptotics for this linear error is going to be bounded by this number, which is 0.86 and so on. So strictly less than 1, which means that qn pi minus pn is going to go to 0 exponentially fast. And that's impossible if pi would be rational, because if pi is rational like a over b, then this quantity over here is at least 1 over b. So the nth root is bounded from above by 1, and that would be a contradiction by saying that its limit is strictly less than 1. So that's a nice proof that pi is irrational. It's a bit harder than the usual proofs, but it gives you a little bit more. It gives you also an upper bound, which I explain in a minute. Now we'll move to the multiple orthogonal polynomials. And the multiple orthogonal polynomials are the polynomials that you get by this type of Rodriguez type formula. So you take this polynomial x to the power n, 1 minus x squared to the power n, and take the nth derivative. It looks like the Legendre polynomial, but it isn't, because I have an x squared over here. The Legendre polynomial would not have this square. It's going to be a polynomial of degree 2n, because this is of degree 3n, and I take a derivative n times, so 2n will be left. And it satisfies some orthogonality conditions. For instance, if I integrate from 0 to 1, which are the zeros of this polynomial over here, and multiply by x to the power k, that will give me 0 for every k between 0 and n minus 1. So I have n orthogonality conditions on the interval 0, 1. But you also have n orthogonality conditions on the interval from -1 to 0, because the -1 is also a 0 of this quantity over here. So you have two orthogonality relations on disjoint intervals, So that's why we call this a multiple orthogonal polynomial. Since we use the Legendre weight, we call it Legendre-Angelesco. And Angelesco comes because these two intervals are disjoint. So this is a multiple orthogonal polynomial for living on two disjoint intervals. The connection with Hermite-Padé approximation is that if we consider this integral with on 0, 1 with this Cauchy kernel over here, and we consider another integral, but on the other interval from -1 to 0 with the Cauchy integral, then you can approximate these two functions f1, f2 simultaneously by rational functions with the same denominator, and that denominator is going to be that particular multiple orthogonal polynomial that I had on the previous slide. You can find the polynomial Qn1 so that it's a good approximant for the first function, and you can find the polynomial Qn2 so that you get a good approximant, a rational approximant for the second function. And the behavior, the approximation will be very close when z tends to infinity, of order n over here and order n over here. We can make the Q, we can specify them there in terms of that multiple orthogonal polynomial. Also for Qn2, there this integral of this ratio, but now on the other interval. And you can also figure out what the error is going to be. The error is going to be such a Cauchy integral with a multiple orthogonal polynomial in the numerator, but integrated over different intervals. So this is the Hermite-Padé approximation. And then what is the connection with pi? I'm going to evaluate these functions in the number I, which is the pole of that function in the denominator. If you work out what the integral is going to be, it's going to give you a combination of logarithm of 2 and pi. And to get rid of the logarithm of 2, I'm going to add both functions, and I get this multiple of pi. The Hermite-Padé approximation has the same denominator, so when I add together, I will keep that denominator, and I will get a rational approximant, namely this in the numerator and the Pn in the denominator for this sum over here, so which is the number pi. And then we can look at the error that we make. And for the error, I can use the Rodriguez formula and do integration by parts. Integrated terms will always cancel in the points -1 and 1 because those are the zeros of this expression over here. So if I do this n times, I move the derivative to this factor, 1 plus ix over here. And this one I can differentiate easily, and that will give me this expression. And this starts to look like the expression for the integral kn that we had before. So this was the kn. So the only thing that changes is that this n and this n should be a 2n, and this n in the bottom should be 3n. So I have to do a little bit more work. So when I go back to the Hermite-Padé approximation over here and differentiate n times, then in this integral, the z only appears over here. If I differentiate the right-hand side n times, I would get this number over here. And then I can use my Rodriguez formula and integration by parts again, sorry. So if I do Rodriguez and integration by parts, this integral, in fact, becomes the integral kn that we had before up to this factor over here. So you see the integral that we were considering is based on Hermite-Padé approximation to two particular functions. And then we can identify the quantities in our rational approximants. The ANs are going to be just that multiple orthogonal polynomial and derivative evaluated at I, which is the 3nth derivative of this polynomial. And I can always express a derivative by means of the Cauchy theorem using residue calculus. So if I take a contour which goes around the point I, which is this point over here, and evaluate this number over here, then I would get the number AN. And remember that the error in my rational approximant was this integral Kn, which was an integral from -1 to 1 of exactly the same expression that we have over here. And then we can do some asymptotics for both integrals, because this is an expression that is very easy to work out using saddle point method. So you look for the saddle point of this expression, and then you deform your contour so that it goes through these saddle points and uses the path of steepest descent. The saddle points are the zeros of this expression over here, and there are exactly 3 saddle points. Okay, and we're going to use this saddle point here for the expression AN, and then we deform our contour which goes around the point I, so that it goes through this point, and that will give the asymptotics for the number A. It's going to be that saddle point evaluated in this rational function, and here you get this other expression. So that will give you the number A. For Kn, it is the same integral, but we're going to use these saddle points over here. So we're going to deform the interval -1 to 1 to a contour that goes through these 2 points, and you will find the number 1 over B. And if you work out what that will give, the measure of irrationality will be bounded from above by this number 23.26. So it's a very high number, but you can improve on the method. Masatoshi Hata in 1993 used a different integral. So he used this rational function and a contour, which is a curve connecting points 1, 2, and 1 plus I. Well, I like to change this a little bit around and make this change a variable. So a shift, a translation, and then the Hn becomes such an expression, which has this polynomial with zeros 0, 1, and I, and a pole in -1. And the contour now will be connecting the points 0, 1, and I. So actually you have a contour connecting these 3 points. And you can deform the contour in any way, as long as you don't go around the point -1, which is the pole. And then again, Hata observed you have that this integral is a linear combination of pi with rational numbers an and bn, but they're now imaginary complex rational numbers. Again, there is going to be some number theory involved. You can multiply the bn by a number, an integer number dn, so that it becomes an integer. And the nth root asymptotics is going to be such a number. And then you can use the saddle point method again to find the A and the B. And what you get is an upper bound for the measure of irrationality, which is now 8.0161, which is a lot better than the 23 we had before. Again, this is not the best. The rational approximation now is over intervals 0 to 1, and now 0 to I instead of -1 to 0. If you evaluate it -1, you would get log 2 for the first integral, and log 2 over 2 minus I pi over 4 for the second interval. You can get rid of the log 2 by taking this linear combination, and for the rest you do the same thing as before. You use saddle point methods. You will get, I'm going to go a bit faster now, and the saddle points will be 3 different numbers, and you can work out exactly what the asymptotic behavior is going to be. This polynomial satisfies again such a Rodriguez type formula. It satisfies a differential equation. You can get the asymptotic behavior of this rational expression, which is going to be a function h that satisfies a cubic equation. And you can figure out where the zeros of this polynomial are going to be. So they're going to be on very special curves. And these red curves over here that I drew, these are the curves for this algebraic expression where two solutions have the same magnitude. So this cubic expression has three solutions in the complex plane. So if you look in the complex plane where two of the solutions are of the same magnitude, you will find this red curve over here, this red curve over here, and the red curve over here. And you see the zeros like to follow these red curves to make a deformation of the contours from 0 to 1 and from 0 to I. So it likes to use such a path over here. I think I have to stop here. Sorry.
Yeah. Thanks, Walter. Thanks for giving a nice talk. Any questions? Any quick questions, please? Yeah, and Walter, your multiple orthogonal polynomials, do they satisfy some reconciliation type things? What sort of reconciliation do they satisfy?
Yes, they satisfy a system of recurrence relations because multiple orthogonal polynomials, let's go back to, so they have two indices. Huh? And if you move up one index, you have one recurrence relation. If you move the other index, the second index, you have a different recurrence relation. So you have a system of two recurrence relations connecting neighboring multi-indices. You can do more than two functions, and then you would have a system of several linear recurrences connecting neighboring recurrence coefficients. Sorry, neighboring multi-indices.
Multi-indices, okay. So it forms array-like expressions.
Yeah. So it generalizes the three-term recurrence relations for orthogonal polynomials, which connect two neighbors, but it's always connecting neighbors. Yeah.
Okay. Thanks, Walter. Any other questions from the participants?
Post
I think Professor Dr. Hemant Kumar has some question.
Yes.
Yeah, Professor Hemant, please.
Please go ahead.
Professor Hemant, any question?
Your microphone is unmuted.
No, sir. I think he has not responded. So you can continue, sir.
Okay.
So thank you, Professor Walter, for accepting our invitation and delivering this talk.
Thanks, Professor Walter.
Okay, my pleasure.
Yeah. So
I will stop sharing.
Yeah, thanks, Walter. Excellent. And so now our next invited speaker is Professor A. Mathai from basically from Canada. And in fact, Professor Mathai is very much known in the circle of the Society of Special Functions. And he has done a lot of work in developing special functions in Indian academic groups. And here, I'm taking a pleasure in inviting Professor Mathai to give his talk on the gamma and beta functions in the complex domain. Over to you, Professor Mathai.
Thank you.
Sir, can you share, sir?
Yeah, please, sir. Professor Mathai,
please
share your.
That is from the share screen. There is a share screen in front of your screen. There is a share screen button.
It's a green color one.
Yeah, it's a green color button.
Maybe
Bottom center, it is going to be the green color button.
Yeah. Bottom center. This one here.
In the bottom center.
Sir, in the morning you did. In the same way you can do that, sir. The morning which you did, that sharing.
See that button here.
It should be there. In the just move your mouse, sir. You just move your mouse so that it will be visible there.
Do you see the mute button on the same row? You can see that share screen button, please.
I had seen it before.
It is the button between mute and leave. It's in the center. Mute is in the left hand, leave is on the right hand. It's in between these two.
Dilip, can you do it from there? I don't see a.
Sir, then I will share. You just speak. Okay, sir.
Yeah. Okay. Can you hear?
Yeah, yes, Professor. Yeah.
Okay. Okay. My talk is on functions of matrix argument. There are lots of results available on functions of.
One second, Professor. Dilip is set to share the screen.
Is it shared now?
No, not yet. I'll just inform you once he shares.
Dilip,
Okay now?
Dilip, can you share his slides so that and let him speak?
I am just sharing. Is this visible?
Yes. Yes, yes, yes. It is visible.
Can you hear now?
Yes, yes, Professor. You will be here. Yeah, you can start, please.
Okay now?
Yeah, yeah. You can start, please.
Okay. I will be talking about functions of matrix argument. When the argument matrix is a real positive definite matrix, we have plenty of results. But when you have a Hermitian positive definite matrix, there are some results available. But on rectangular matrices in the complex domain, as well as multivariate cases in the complex domain, there are not many results available. So I have a forthcoming book on multivariate analysis, and I have included a lot of results on the complex domain. Special functions with matrix argument. The argument can be square matrices, Hermitian matrices, rectangular matrices, all in the complex plane, complex domain. So this talk will be starting with gamma and beta functions in the complex domain. And then if I have time, I will go into the, this is a non-singular case. I have also plenty of results on the corresponding singular case. So I will start with gamma and beta functions. There are lots of general results, and the notation that I am going to use, small letters will be used for scalar variables, capital letters will be used for vector matrix variables, and a tilde will be used on the top for complex variables. Constants, I will not use tilde. Constants, scalar constants will be ABC, etc. Matrix vector constants will be capital ABC, etc. I need the Wedge product of differentials. The Wedge product of differentials for a P by Q matrix is this, the wedge product of all the differentials in that matrix. And when it is symmetric, real symmetric, the wedge product will be like this, P into P plus 1 by 2 differentials only. And in the complex domain, any matrix can be written like this. These two are real matrices, I is square root of -1. Then the wedge product of differentials in x tilde will be defined as dx1 wedge dx2. x1 and x2 are the real parts, real and complex parts. And I will be using this notation also. Determinant, this means determinant of A with the absolute value of the determinant of A, or the modulus of the determinant of A. Now, when I write like this, integral A to B fx dx, where A and B are constant matrices, and this means this, which means A is positive definite, B is positive definite, x minus A is positive definite, B minus x is positive definite. And the corresponding quantities in the complex domain also. I will need a few results on the Jacobian of matrix transformations. And you can find these results and proofs in my book, 1997 book on Jacobians. I am only giving the results on the complex domain. So if you have y equal to ax b, where a and x and y are on in the m by p by q matrices, a and b are constants, then with the determinant of a not equal to 0, not determinant of b not equal to 0, then dy, the wedge product of products or differentials in y, will be absolute value of the determinant of A star. A star is the conjugate transpose of A raised to n, and absolute value of the determinant of B star raised to m dx. And the another result that I will need is if it is a P by P.
The sound in.
Cannot you hear? So if y is AXS star, that means then dy is equal to determinant, absolute value determinant of A star raised to P dx. And this is another result that I will use. That is for this is a Hermitian positive definite matrix. This notation means positive definite. I can always represent it in terms of a lower triangular matrix with real and positive diagonal elements. And this is it, conjugate transpose. Then the differential element will be connected like this. Tjj is the diagonal element raised to 2 raised to p minus j plus 1. This is the important result that I will be using. That if I have X a P by Q matrix, P less than or equal to Q and of rank P, full rank P. So we have PQ real scalar complex variables. And S I take it as XX star, so that this will be positive definite. And if I make a transformation X equal to T is lower triangular matrix, U is a unitary matrix, then I can connect dx with ds. S is P by P, Hermitian positive definite, X is P by Q. So the connection is dx equal to pi raised to pq by gamma p of q. Gamma p is a matrix variate. It's a complex matrix variate gamma. You find it here. So this gamma p is a complex matrix variate gamma. it is pi raised to p into p minus 1 by 2 gamma q minus 1, etc. gamma q minus 1 differing by q minus p plus 1. Okay. Now, by using that result, we can evaluate this type of an integral. This is actually gamma type integral with a complex domain. I use that Jacobian there, and it will break down into or break up into products of these types of integrals. This is real integral, and here it is the absolute value of Tij or I greater than j. Then you see that the Tjj integrals will become gamma integrals like this, real alpha greater than j minus 1. And for j is equal to 1 to the final condition will be real alpha greater than p minus 1. And the gamma products will be like this, gamma alpha, gamma, etc. Now, that exponential integral is, this is the form. Tij is a scalar complex variable. That's a real part. It's a complex part. So these are minus infinity to plus infinity, k1 to 2. Then, of course, the Jacobian will be like this, or the differential element will be like that. And this integral, of course, standard integral, you can go to polar coordinates and evaluate, and that is pi. Therefore, the product involving those exponential integrals will give pi raised to p into p minus 1. Therefore, the gamma integral will be like this, and this is the notation that we use. And this I call it the complex matrix variate gamma, generalization of the ordinary gamma. Complex matrix variate because it is associated with this type of a gamma, matrix variate gamma integral. Okay. Now, we can define, these are the basic building blocks. We can define matrix variate, complex matrix variate beta function as the ratio of these gamma functions corresponding to the scalar case or corresponding to the real case also. We can construct integral representations for that beta function in the complex domain, matrix variate beta function. This is this corresponds to the scalar integral. It's in the complex domain, it will be this raised to alpha minus 1 and alpha minus p. In the scalar case, it is alpha minus 1. Here it will be alpha minus p. In the scalar case, here you have beta minus 1. Here it will simply go to beta minus p like that. So these two are type 1 beta integrals. And next to 2, these two are type 2 beta integrals. Here, of course, the range is null to identity matrix. That means all the eigenvalues of Hermitian positive definite matrices are real. And here the eigenvalues will be between 0 and 1, or in the open interval 0, 1. Here, of course, simply positive definite, Hermitian positive definite in type 2 beta case. So you have corresponding to your univariate case. In the univariate case, you have alpha minus 1 here and alpha plus beta. That remains the same. And derivation of it, I will derive 1 or 2. So we start with the gamma integral. So this is the gamma p of alpha, gamma p of beta. So I can write this integral form and this integral form, or in that case, you have a double integral over x and y. X positive definite, Hermitian positive definite. Y is also Hermitian positive definite. And we have this joint integral. Now we make a transformation. I can make a transformation of 2 matrices going to 2 matrices, or I can use a conditional argument. I can make one matrix go into one matrix with the other one fixed. For fixed y, I can make u equal to x plus y, so that one variable go into one variable. So this I can also rewrite it like this, like that. And this u raised to 1 by 2 is Hermitian positive definite square root of the Hermitian positive definite u. Okay. Because we want the square root as well as the original matrix to be in the class of Hermitian positive definite matrices. Now we take this transformation, make this transformation. Then according to my lemma 1, I have the different elements connected like this. That is from lemma 1. And then I have the one, I just integrate out this u. This is actually a gamma type integral for u in the complex domain. So that gives you gamma p of alpha plus beta. And the remaining part is this. So this is one of the representation for that type 1 beta in the complex domain. For the next result, I can use y equal to I minus x. Then dy will be minus 1 raised to p squared times dx. That minus 1, this will be absorbed by reorienting the new variables. So you don't have to worry about that. And then the parameters will be simply interchanged. Alpha and beta will be interchanged. That is the result. Now, for getting from type 1 to type 2, you can go through a transformation of the following type. Here, if x is type 1, and if I make this transformation, u equal to I minus x raised to minus half x minus half, I can split this x raised to half x raised to half, absorb one part here and absorb the other part here. So I will end up with this u equal to x minus 1 minus 1 x minus 1 minus I, the whole thing raised to minus 1, or u minus 1 is equal to this. Now I can use that Jacobian on the inverse. So therefore I will get, this will be the result. So the dx is connected to du like this. Now you just make the this part will be corresponding substitution, and then you will end up with type 1 will go to the type 2. One case from 1 you will get 3. 3 is type 2. Now you make an inverse transformation. This is the Jacobian or the corresponding differential element. Under this transformation, you will see that in the type 2, the parameters will be interchanged. Thus, you can get all those standard results that I mentioned. You can also derive the following results. If you have x type 1, then of course this is already done. If x is type 1, then this is type 2. If u is type 2, then this is type 2 again in parameters interchanged. If u is type 2, then this corresponding to this transformation here. So 1 minus I plus u raised to minus half u, I plus u raised to minus half, that will go to a type 1, alpha and beta. Now, I'll make a little change here. A scaling matrix is introduced. It's again a positive definite, Hermitian positive definite matrix. So in that scaling, I can apply the first result on Jacobian and evaluate it. You will get this. From there, I will get this identity here. This is a very important identity, which you can use in many cases when you want to integrate complicated integral, where in the integrand, you have a factor with a negative exponent sitting. Suppose that you have a factor here with a negative exponent sitting. That factor can be replaced by using this as in terms of an integral. Then you will see that the original integral becomes simple and you can integrate. It will also introduce one more integral which you can integrate also. So, and you can also create statistical densities out of this. So here, this part is a statistical density, because you can see it's a real valued function, even though the argument is a complex matrix. It's a real valued scalar function with a total integral 1. So that is the definition for a density. So it is a statistical density function with a matrix argument, a Hermitian positive definite matrix in the complex domain. Okay. Now I will go into, well, a particular case of that, with that B replaced by sigma minus 1 for some sigma Hermitian positive definite. You have the Wishart density, complex version of the central Wishart density, and the real central Wishart density is the most important density in multivariate statistical analysis. So this is the corresponding one. Now I look at some other properties. These are also connected to various types of problems in different areas. I will connect it to Kratzel integrals, a generalization of that. Also, we can connect it to reaction rate probability integral, generalization of that. Also, we can connect it to fractional integrals in the complex domain. Okay. So let me consider x1 and x2 as with associated functions f1 and f2 with a joint function, the product. In statistical terms, these are actually, when we say x1 and x2 are statistically independently distributed with the density functions f1 and f2, then the joint density will be the product. And if x1 and x2 are gamma distributed, then the joint density will be of this form. Okay. Well, in mathematical terms, you don't have to worry about this constant part. You have a function x1 associated with some f1, x2 associated with f2, and the joint function associated with this, then all these properties will hold. Now, if you consider a ratio of matrices, how do we define a ratio of matrices? I can define a symmetric ratio like this. This I can call it ratio of x2 over x1. That is x2 raised to 1/2, x2 raised to 1/2 here, x1 raised inverse. So this is a symmetric product of matrices, and it is the form of a ratio because this is the inverse matrix sitting here, and here is the product. Now this is again a symmetric product of two matrices, x1 and x2. But x2 raised to 1/2, x1, x2 raised to 1/2, or I can define the other way around. Here also I can define the other way around as the ratio. But these ratios are quite interesting. The statistical properties as well as mathematical properties are quite interesting. Now, you have the Medlin here. If f1 and f2 are functions such that these integrals exist, these are called the Medlin transforms. x1 raised to s minus 1, f1, x1, x2 raised to s minus 1, f2, x2 integrated 0 to infinity. So when the integrals are convergent, we call it the Medlin transform of f1 with parameter s, Medlin transform of f2 with parameter s. Correspondingly, I have defined something called M transforms and M convolutions. So I will give the parallel and then give the interpretation also. So here, if you have scalar variables, then you can see that if you take the ratio x2 upon x1, this is the corresponding Jacobian, and you go through, and if you want to evaluate the function corresponding to u1, this is the function corresponding to u1.
Professor, you have 2 minutes time, please.
Yes.
You have 2 minutes time, please.
Only 2 minutes?
Yes, Professor.
So this is the corresponding results we have. I call M convolutions. For products, you have many different functional forms. and ratios we have plenty more. And we can also connect it to fractional calculus, fractional integrals. Actually, if I take one of the functions as a type 1 beta, well, here is the Kratzel integral and the generalization of that. In the matrix case, I can get the generalization. This is Kratzel integral as well as reaction rate probability integral. And we have the generalization of that in the matrix case. And if I take a type 1 beta as one of the functions and the second function an arbitrary function, and if I calculate the density of this or the M convolution of this, you end up with this. And this is actually the this is the LLE-Kober fractional integral of order alpha and the second kind with parameter alpha. So I have plenty of corresponding results also. So the connection between fractional integrals and the statistical distribution theory in the complex domain is already established. So I have a series of papers in linear algebra and applications. Starting from 2013, you will find a lot of papers there. So those connections are available from there. So I will stop, since the time is up, I will stop here. Is there any question?
Thank you, Professor. Any questions, please? And in fact, I have a question. So basically, for this univariate gamma integrals, we have in the real case, we have the Bohr-Mollerup theorems, and in the complex case, we have Velan's theorem and all. Similarly, for this matrix variate case, using their positive definiteness, do we have any theory exist on that?
Positive definite, yes, we have plenty of that, plenty of results. And some of the results are available in my 1997 book, and the remaining ones will be coming out in 2022.
Okay, very good.
The fourth is the main book from Springer. Springer will be publishing it. It's a big book, about 2,000 pages, and it will contain a complete collection of the results in the complex domain.
Okay. Thank you, Professor. Any other question, please? If there are no questions, I take this opportunity to thank Professor Mathai for his nice talk and his excellent information about this multivariate gamma integrals. And now I think his talk comes to an end. And shall I ask Professor Dimitri Karp?
I'm here. Hi, Swami.
Hi, Dimitri. How are you? Yeah. How are you? Fine. Yeah.
Everything fine. I can start.
Yeah. So can you start sharing your screen, please?
Yes, I will try now. 1 second. Can you see it?
Yeah. It's available. Maybe.
Yeah, it is visible, sir.
It's visible. The full screen. So maybe you can make it as a presentation one so that it will come to the center of the screen.
Well, this mode is okay because maybe I will write something on it.
Yeah. So now the third invited speaker in this session is Professor Dimitri Karp from Holon Institute of Technology, Israel. And I know Professor Dimitri Karp for several years, and his contribution to generalized hypergeometric series, Q hypergeometric series, and basic hypergeometric series is well known. He has studied a lot of work in this direction, and I don't want to stand between his talk and the audience. So, Professor Dimitri Karp, please, you can give your talk on multi-term identities of generalized hypergeometric function, evaluated unity, summation of psi series, and subtheorem.
Thank you, Swami. Thank you for presentation. Okay, so the title has been already said, and I want to add that this is based on different papers joined with Elena Prelepkina, Asena Chetinka, Alexei Kuznetsov, and Sergei Kalmykov, different parts with different people. And well, I'm sure all the audience is familiar with the definition of the hypergeometric function, but let me repeat briefly. So if we have a series such that the neighboring terms ratio is a rational function of the summation index, like here, then it is easy to see that this series is proportional. Actually, there must be a constant here, constant multiple, the series of this form, known as the generalized hypergeometric series. This is a standard notation for shifted or rising factorial, defined here. Well, and I will use this vector notation. So A is the vector of parameters, B is a vector of parameters as well. Well, I'll basically be interested in Z equal unity. So, and the famous celebrated formula due to Gauss says that in this case, we can evaluate F21 as simple ratio of products of the gamma function. This formula, among other things, shows that it gives analytic continuation of this function as the function of the variables A, B, C, and shows that other than obvious poles at C equals 0, -1, and so on, which are clear from the series definition, you also have singular hyperplanes C minus A minus B equal 0, -1, and so on, negative 0 and negative integers. Unfortunately, or not unfortunately, but the truth is there is no such explicit summation in case of higher order hypergeometric functions, but there are different transformations that also give you a chance to make analytic continuation and see the singular sets in the higher case. The F32 case, there is a famous Tamae. Actually, first transformation comes from Kummer, but the whole group is called Tamae group. And here is an example. This formula and these two formulas give transformation for F32 evaluated at unity. From this point, I will omit the argument if the argument is unity. There is argument unity here. And the convergence domain of the series on the left and the series of the right are different. So indeed, we can get analytic continuation from this formula. We also see that, again, the set like the parametric excess, the sum of the bottom parameters minus the sum of the top parameters equal to 0, -1, and so on. This expression is a singular hyperplanes for this function of, in this case, 5 variables, 5 complex variables. There is also, let me mention also that for F32, there are 3-term transformations, also known as Tamae 3-term transformations. An example is given here. They have been studied from different viewpoints, like the group structure and so on. This is all studied. And this is for unrestricted parameters. So parameters of this F32 are 3 parameters. In a higher order case, if P is greater than or equal to 3, this function has no 2 or 3-term unrestricted transformation. At least there are no known ones. But if we impose certain restrictions, then we do have a lot of different formulas. And the typical restrictions are conditions like balancing, which means like the sum of the bottom parameters, this parametric excess, the sum of the bottom parameters minus the sum of the top parameters equal 1 or equal 2 sometimes. So kind of balancing condition. Well poisedness means that the sum of each pair of bottom and top parameters is a constant. Other conditions are integral shifts, like you have, for instance, parameter A plus 1 on the top and parameter A in the bottom. So this is a unit shift case, or it could be N here, the N shift case. Well, these are the typical conditions. And then in this case, there are famous transformations due to associated usually with the names of Watson, Whipple, Dixon, Dougal, and Bailey. Well, other names as well, but these are most classical ones. Well, each such result gives certain information and gives probably analytic continuations, but for restricted parameters. In unrestricted case, we still have, in generally for this function, we have p plus 2 term relation, and I call them multi-term relations, and some of them are pretty obvious. In fact, these are some examples. One comes from, well, sorry, not one. 3 of them come from actually from the properties of Meyer G function. I will not go into detailed definition. I will not need it in this talk. Let me just say that you can just think of it as this combination of hypergeometric function. Let this be the definition of this specific type of Meyer G function. And it is known that its asymptotics as x goes to 1. I use p plus 1 here because I will use instead of p plus 1 in the next formula. Its asymptotic has this form as x goes to 1, where nu is the sum of parameters c, in this case top parameters of G function, minus the sum of the bottom parameters. This is well known, and this will immediately lead to multi-term identity. Let me just mention that I will use this notation. If you see gamma of a vector, that means product. This is very convenient. And if you see this square brackets with the index, that means this index is omitted from the vector, like here. So there is no AK here. From k minus 1, which jump immediately to k plus 1. So, and if I simply set x equal 1 here, and I assume this nu minus 1 is positive, that means I will get 0 here. And I immediately get a multi-term identity, this one here, this identity, simply by setting x equal 1 and knowing the asymptotic of G function. This is an obvious identity, but for example, its particular cases for p equal 2, equal 3 appear in the literature under different names. For p equal 2, it's one of the three-term Tomei relations. For p equal 2, for p equal 3, it appears an example, for example, in a paper of Darling, well, back in 1931, I guess. But all of these are pretty obvious. I couldn't find actually the general identity of in this general formulation, but obviously it must be somewhere because it's a direct consequence of definition of G function. So we have this multi-term identity. Unfortunately, it does not give analytic continuation in parameters because the convergence domain of each function here is the same. Each function in the sum has the same convergence domain. By changing notation, I can also rewrite this identity, the same identity, in this form. And I need this form to compare it with another identity, which you will see right now. If we use a G function in a little bit different way, if we write hypergeometric function as a generalized Celtier transform of G function, again, a simple formula obtained by termwise integration and using some basic property of G function, namely the Mellin transform of G function is the power, we get this simple representation. And if we plug into this simple representation, this definition or this expansion of G function and integrate, we get another identity, which has this form. So I wrote my first identity in this form is precisely to compare with the identity obtained in this way. This was found by Norlund. The proof is different, and then it was rediscovered by Wimp, and also he has a different proof. But in fact, all of this is obvious from definition of G function. I still don't know, and that's still a wonder for me, if these identities are actually the same, if it is possible to get one from the other by certain smart compositions. They look different, but if in fact one can be obtained from the other, I don't know. We can also use a little bit extended G function to get another identity. If instead of G function of the form G P0 PP, we use a slightly more general G M N, say PP with M plus N equal P. If we use this G function and expand this G function, we can get another identity, which I don't know, I couldn't find it in the literature, other than for P equal 2 and Mn equal 1 and 1. This is known. We get this relation. There are certain convergence conditions here, and also the proof is pretty obvious, integration using definition and expansion of G function. So we have a certain the number of terms here is equal to actually to P. So M plus, well, it could be even greater than P, but the minimal number of terms is P. So M plus N can be greater than P. So sorry, not necessarily equal. We get this a little bit different kind of identity because we don't give 0 on the right hand side, but we give certain ratio of gammas. And depending of evenness or oddness of this P minus M minus N, we get evaluation at 1 or at -1. Okay, but again, this identity doesn't give you a way to analytically continue this function as the function of these parameters. Regarding this analytic continuation, it has been done by Norlund. Then there was some rediscoveries and some additional information in the papers of Buring and in the papers of Srivastava and Saigo, dated beginning of 90s. But all these results, they have kind of they have this function equal to some P plus 1 fold summation on the right. So we do have analytic continuation, but the price is we have the P plus 1 fold summation. So for big P, we have really a multiple sum on the right. But actually, there is a formula which is implicit in Norlund's paper, which can be obtained by certain combination of his formulas. It's not given in this form in his work, which gives analytic continuation and representation of this function at 1 as threefold summation. And this number 3 is independent of P. So you always get, for any P, you get threefold summation. And the coefficients are extremely simple. They are very simple hypergeometric polynomials, unlike the coefficients in the well-known formulas due to Norlund, Buring, and others. So why I say threefold, because you have one summation here, and this sum is also a sum of n terms. So in total, you have certain threefold sum of some Pogamer symbols or gammas. And this formula indeed gives analytic continuation because the convergence of this series is under this condition, while convergence of the series on the left is under this condition. So the convergence domains are different, and you get analytic continuation of this function as the function of these two vectors A and B. Actually, this condition can be removed because you can separate this into a polynomial and another series. So you can kind of break it into pieces, and you can always substitute this condition. Like if you separate first m terms, you get condition like plus m greater than 0. So, and m you can choose arbitrarily, so you can always get this. So in principle, this formula gives analytic continuation for any parameters. You just need to separate first m terms if a1, 2 are small, are negative, let's say. Well, simple, but I haven't seen this before. Well, if we use this multi-term identities, they have always kind of term of this type, which becomes infinity if one of the differences here is negative integer or 0. But actually, the function on the left does not become infinite. So there is a certain degeneration here, and you get kind of parameter derivative of hypergeometric function, not in this identity, but in all the above one, also in this one, but in the above one, above ones. And what do you get? You get certain type of psi function. And in this case, you can find actually some kind of, well, you can call them transformation. They're not really summation formulas. They're more like transformation formulas for the series in terms of psi function, so d gamma function. So psi is a logarithmic derivative of the gamma function, the standard d gamma function. For instance, we get this unusual formula. So this sum, again, this is a product. This is a product C1 k times C2 k and so on up to p, up to Cp k and so on. So this is a product, and this is the sum over all components of the vector d. This is the sum over all components of the vector c. So this psi series can be converted into hypergeometric series or combination of hypergeometric series written here. So quite unusual. I haven't seen this before. So this is obtained by degeneration of some of the multi-term identities above. By the way, I forgot to mention that the results up to that point are published already in this reference. This is still work in progress, jointly with Asena Chetinka. And we also use different identities to get the summations, and comparing them, we get also another multi-term relation for hypergeometric without psi, which doesn't look like a particular case of any previously known multi-term identity. This identity is written here. It has certain special condition that one of the bottom parameters must be positive integer. One of the bottom parameters is positive integer, otherwise parameters are free. Then we have this very exotic identity. It's also p plus 1 term, just like the identities above. It has p plus 1 terms in it. Okay, this is work in progress. Now let me mention some identities for terminating series. This we get from this duality relation, which we derived also couple of years ago, published only recently with Alexei Kuznetsov, this duality relation. There is certain notation here. M is an integer vector, N is another integer vector. Big M, big N are sums of the components. Then you have obvious M minimum, M maximum. And this number P is a certain number derived from the sums. So it can be -1 or this maximum. Then the following identity holds. This actually I have shown in last year's talks. I don't expect you to remember, of course, but this was already in last year's talk. But unlike last year, now I can also give explicit formula for these coefficients Pj, which are actually a double sum of certain terminating hypergeometric functions. So we have a terminating function here. This is a negative integer, and these coefficients are explicit in terms of this function. Okay, now by setting z equal 1 and certain manipulations to make everything finite, we can get two identities from this. One of them is that these numbers, Bj, satisfy, they are complicated, but they satisfy pretty simple formula. The sum of these numbers, this sum is kind of natural because these numbers are actually defined for k in this range. We obtain this simple formula. We obtain this where nu is simply sum of b's minus sum of a's. Well, I'm not sure if it's any useful because you get here triple sum of terminating f to r minus 1 functions with even number here. It's a triple sum. So here is one sum, another sum, and then there is one more sum here. A simpler left-hand side is obtained in the following proposition. We have a single sum of terminating hypergeometric equal to certain polynomial of k. K is this parameter here. It's free. Any k we can take greater than this number. And this polynomial, first of all, if this number p equal maximum minus 1, m minus n minus r plus 1, if this maximum is minus 1, then we simply get 0 here. So we get a pretty simple identity. If p equal 0, we get simply 1 here. Otherwise, we get a certain combination of Bernoulli polynomials. It's given in terms of this big Q. And this big Q is has this explicit form. This big Q has this explicit form where Bj is the Bernoulli polynomial. Well, there is a recurrence relation, but actually it's all of this is a simply so-called exponential formula. So the Q small are coefficients in the power series expansion in terms of Q big. But of course, you can use this recurrence to compute any Q that you want. For instance, the first several of them, Q1 is equal simply big Q divided by 2. Q2 is equal this expression. So it's quadratic expression. Then you have a cubic expression and so on. And this identity I believe to be new. Let me finish by mentioning some Q analogs. Well, here is the standard Q notation, Q shifted factorials. We also use both positive and negative indices. And well, more recently, we discovered Q analog of this duality relation, which I have shown. It's a rather complicated formula. So we have this sum of products of basic hypergeometric functions equals sum of polynomial in Z. And the coefficients of this polynomial, well, it's Laurent polynomial. It may have negative powers. the coefficients are also given explicitly, also in terms of terminating basic hypergeometric series phi to r minus 1. And we, in a similar fashion, we can use this identity to derive some, well, these are some examples of this right-hand side. So for small m and n, the shifts, this m and n, if they're small, then the right-hand sides are usually quite simple. You can see the right-hand side can be like this, or like this, or like this. So this just are some examples. And we have some corollaries. Actually, this gives the analog of this formula that we previously derived from Meyer-G function. We have this sum of basic hypergeometric non-terminating equals this terminating, this finite expression in terms of these beta keys. In particular, if this parameter t is 0 or negative, we simply get 0 here. So when we get 0, this is exactly the analog, Q analog of this identity that I have shown, which we got from Meyer's G function. This time evaluation is not, the evaluation is at the number W, and the number W is this expression here. The number is this expression here. And finally, also we get the Q analog of the second, the relation, well, of the relation for terminating series. We again have the sum of terminating series equals certain expression of this form where this Q, P and PP are again some recursively defined polynomials, but in this case, no Bernoulli polynomials appear. Instead of Bernoulli, you just have this explicit polynomials of this form. Then you get a certain recurrence relation, which allows to define this Q small, certain recurrence relation, which allows to define this P small. And then you put this all together and you get that the sum, finite sum of terminating functions, basic hypergeometric function equals this expression. Again, if these parameters equal -1, we simply get 0 here. So for a large range of parameters, the sum simply equals 0. Well, my time is over, so I thank you for attention and I stop here. Thank you very much.
Thank you, Professor Dimitri. Any questions?
Just something
please?
in the chat.
Yeah, any questions, please?
Sorry, I cannot hear anybody. Wait.
Are there any questions, please? Yeah, if there are no questions, we thank Professor Dimitri for his nice talk. And
Thank you.
Thank you. And thanks to all the participants for this session. I give this to Professor Dilip. Please.
Thank you, Professor Swaminathan, for chairing this session. In fact, we had a very wonderful session of Professor Walter Vanasche, who talked on number pi, and then Professor Matai talked on gamma and beta functions in complex domain, and finally Dimitri Karp talked on generalized hypergeometric functions. So on behalf of the Department of Mathematics and all the participants, I extend our sincere gratitude to Professor Swaminathan and Professor Vanasche and Matai and Dimitri Karp. So thank you very much.
Thank you
for your timely presentation. So, dear participants, our second session has come to an end, and now we will be having our third session at 2:30 p.m. today. And please note that we will be having our R.P. Agarwal Memorial Lecture today at 6 p.m. The R.P. Agarwal lecture will be delivered by Professor Ken Ono. So please be on time on that sessions also. The attendance will be shared in the afternoon sessions. And the paper presentation sessions will be from 4 to 5:50 for today's session. So thank you very much. And we will be coming back at 2:30 for the third session. Thank you all.
2 or 2:30?
It is
Exactly.
2:30. 2:30.
2:30.
Yeah.
Thank you.
Thank you, sir. Thank you.
Okay, 2:30 Indian time. Yeah.
Yeah, all timings are Indian time.
Okay.